of having this conference on a permanent basis, I would say. And also for his kind contribution and support during our doing mathematical physics. So the title of the talk is Exponential Decay, Quantum Mechanics, and Continuous Monitoring. So this is the abstract of my talk, but you know, I didn't want to say everything what I can about the abstract. I'd like to indicate some important keywords over there. Of course, I will be talking about exponential decay scenario in quantum mechanics. Some effects are going to be discussed, but the most important thing from the mathematical point of view, I will be dealing with the variant of the Nedeljkov-Kolmogorov one stable central limit theorem. So if you see such kind of keywords, I think it's more or less clear that after some work you can do what I did. So the contents, the outline of the talk is the following. First, we'll discuss some radioactive decay in radioactive decay in dating. Then I will explain a couple of words about quantum measurements. Then we'll deal with survival probability. And then I need to introduce a very important concept, which is called continuous monitoring. And after that, we'll discuss briefly quantum Zeno effect, quantum anti-Zeno effect, and something which is happening in between, the so-called exponential decay. And then hopefully I finish my talk by showing some examples where this machinery can be applied. Okay. So first, we need to understand whether exponential decay is available. There is a very strong evidence, experimental evidence, that it is the case. For instance, let's take a look at the radioactive decay of isotope of carbon, C14, and we know that the half-life of this decay is approximately 5,730 years. It's about the life of a culture. So applying this radioactive decay scenario, apparently we can find out what was going on in our history, and we can actually say something definite about situation maybe 50,000 years ago. So we strongly believe that at least for a long period of time, exponential decay for isotopes for C14 is available. It's more or less clear that exponential decay for isotope carbon-14 has something to do with quantum mechanics. And therefore, the question is whether we can say something definite about exponential decay scenario in quantum mechanics. In order to start talking about this, I'd like you to take micro course in quantum mechanics. And the story is like this. We're dealing with a quantum system. The system is rather interesting. There is a Hilbert space of states. There is a Hamiltonian, very important operator, which is responsible for the behavior of the system in time. And there is a state. I will call the state phi. So the story is very simple. We have a self-adjoint operator and the state, and nothing else. If you have those two objects, apparently we are done. And this is the basic thing we are going to discuss today. So if you have a self-adjoint operator, which apparently is observable, you are trying to understand what values can this observable have. So you conduct an experiment, and apparently, after working with the data, you will get some kind of measure. And this measure is responsible for the distribution of data obtained when you conduct the experiment. So, and this measure will play a very important role in the whole talk and can be obtained as follows. So suppose we have a self-adjoint operator. The self-adjoint operator can be represented as a spectral integral with respect to the spectral measure. And then here mu sub phi is nothing but as a scalar spectral measure associated with the state. So we have just a probability distribution and nothing else. Self-adjoint operator, state, probability distribution. And if you have a probability distribution, you can switch into a different language. We can start talking about probability theory. So we've got some random variable distributed in accordance with the distribution of the spectral measure, and that's it. So either self-adjoint operator and a unit vector, or just a random variable associated with the corresponding system. So the thing I'm going to talk about is going to be the so-called survival probability of the state. So if I start with the state will be developing in time in accordance with the Schrödinger picture. Apparently here one is supposed to write minus, but I decided not to do that. So this is not a talk in physics, but in mathematics. So we have a unitary group of strongly continuous unitary group of operators, and we have a state. We take the corresponding quadratic form, and then take the square of this quadratic form. And the physical meaning of this is so-called survival probability. In other words, if I want to look at the system at the moment of time t, then I will find the probability that the system is still in the initial state. Otherwise, it may be in different states. So it's more or less clear that this probability should go to 0 sometimes. And the question is how fast this survival probability may decay. For instance, can this decay be exponentially small in time? And the answer is yes, but in this case, the spectrum of the operator must fill the whole real axis. And therefore, if you require that your Hamiltonian is semi-bounded from below, or it has a gap in the spectrum, or for instance, it has some eigenvalues, discrete spectrum, so there is no way to have exponential decay in quantum mechanics. So we have some kind of contradiction. From one point of view, we believe that there is exponential decay in quantum mechanics. From the other point of view, we don't believe in that because of this result. The question is what to do. There are two possible ways to overcome this difficulty. The first one, probably you can start doing quantum field theory. I'm not ready to do that. And the other thing, you can modify the measurement paradigm. What do I mean by this? I will be looking at my quantum system frequently. So the standard situation is like this. You prepare a state and you wait for a while and then see what's happening. But now I will be watching what's happening at some moments of time, T1, T2, T3, Tn. And in accordance with the measurement reduction postulate in quantum mechanics, the probability to find the system in the initial state apparently will be the product of such kind of probabilities. And it is not the same as the probability of P of t. The question is, what is going to happen with this product? So here, P of t is the survival probability. So apparently, one can start talking about frequent measurements or continuous monitoring. So I'm just going to the corresponding limit. So for instance, we take the probability to find the system at in the initial state at the moment of time t divided by n, and then multiply by n and go to the limit and see what the limit is. You know, there are different scenarios, and somehow quite unexpected thing is due to halving. And halving understood that just watching at the system, you can stop the evolution. So if I watch continuously on the system, I can hypnotize the evolution. And this observation is due to halving. And apparently, the corresponding result has been extended by Misra and Sudarshan. And nowadays is known as a quantum Zeno effect. Apparently, the simplest variant of the corresponding statement is like this. Assume that the Hamiltonian of the system is a bounded operator. Then, if you watch the system in a continuous way, there will be no evolution at all. So this limit is 1. I decided to show you where it comes from. So the idea is like this. First, let's take a look at the quadratic form associated with the corresponding unitary group. It is nothing but that Fourier transform of the measure I was talking about, spectral measure I was talking about from the very beginning, or for a probabilist, at the characteristic function of the random variable psi. So now, suppose I decided to take a look at identically distributed independent copies of my random variable. And then I'd like to use the law of large numbers. You know, if you have a bounded operator, of course, you have the first moment, you have all moments of the measure. And therefore, I can apply the strong variant of the law of large numbers. So this guy will go to the mathematical expectations almost surely. Now I'm looking at the corresponding amplitude. This is the thing, the exponential, the characteristic function of psi at the moment of time t divided by n to the power n. And then since so this is the product of such kind of things. But you know, our sequence has the same distribution. That's why instead of psi, I can write psi sub k, they have the same distribution. And now I can use the fact that those guys are independent and interchange the operation of taking the product and the mathematical expectation. But if I have a product of exponential functions, I will have the exponential functions of the sum, but this guy goes to the mathematical expectation. And that's why I'm, because I can apply the dominated convergence, I will get the mathematical expectation of something which has absolute value 1. And that's why this limit is going to be 1. Done. So this is the simplest explanation of the quantum Zeno effect. So we'll say, apparently this result can be extended. For instance, if our operator is unbounded, every state from the domain operator will be a Zeno state. Moreover, every state from the domain of the quadratic form of the operator will be a Zeno state if the operator is semi-bounded. If it is not, so just take a look at the domain of the square root of the absolute value of the operator. So this result says that necessary and sufficient conditions are available to ensure that we are dealing with a quantum Zeno effect. So this statement says that the distribution for the random variable should have light tails. And then we'll have a quantum Zeno effect if and only if. Apparently, sometimes it happens that the corresponding limit is 0. So I have a quantum system, I look at the system, and the system disappears immediately. There are some theorems where conditions close to necessary, sufficient conditions close to necessary are discussed. I'm not going to do this now. And now the most interesting thing, it may happen that this limit is apparently an exponential function. So this thing is going to be decay as exponential function. And in this situation, if it happens, we say that our state is a resonant state, and we are dealing with an exponential decay in quantum mechanics with the decrement alpha. So it's not that difficult to understand when such kind of scenario takes place. So the observation is the following. Assume that the distribution function of the initial random variable psi, I was talking about from the very beginning, belongs to the domain of normal attraction of one stable law. Then phi is a resonant state. So I'm just I'm using language from probability theory, but this means the following. So assume that the average of those guys plus some additional constant that are taken in a clever way, that this random variable converges to one stable law in distribution. So this law is supposed to have this characteristic function of this way. And if it is the case, then the amplitude multiplied by this additional factor will behave like the one stable distribution. And if you take the absolute value, this logarithmic terms, because of the presence of this I, will disappear. And we will see that the absolute value of this guy squared goes to the exponential function, and we have a decay. So Gnedenko and Kolmogorov proved a series of very important results, but apparently it is known that if the tails are heavy in this sense, that the probability that xi is greater than lambda multiplied by lambda approaches one constant from the one side and the other constant from the other side. If those constants are different, then this limit is going to be the exponential function like this. So this is a characteristic function of the Cauchy distribution. And therefore we have a exponential decay scenario under those assumptions. I didn't present the result in full generality. I don't need it. So the question is how to apply this thing in operator theory. If we are talking about differential operators, usually we need to pose some boundary conditions to make sure that our operator is going to be, differential operator is going to be a self-adjoint one. Usually we have a symmetric operator, minimal operator, the adjoint operator where no boundary conditions are posed. And the idea is just to study a situation when the initial state is taken from the domain of the larger operator and see what happens. Let's see. We know that if the function is from the domain, then we have Zeno effect. But what is going to happen if the function belongs to the domain of the adjoint? So let me recall you a very simple picture. I have a symmetric operator. It has a domain like this. The adjoint operator has a huge domain like that. And the self-adjoint realization of the differential operator has this domain, which is something in between, okay? So a little thing, a huge thing, something in between. So this is mathematical physics, by the way, operator theory. So now I'd like to talk about a couple of examples. So the first example, my examples are very simple in order to make sure that there is a chance to understand what's going on. So I'm looking at the realization, self-adjoint realization of the second differentiation operator on the positive semi-axis. And I will pose two boundary conditions. Dirichlet, or say Neumann, maybe the condition of Robin type, but it's easy to me to discuss those two. So this is the Friedrichs extension of a semi-bounded operator. And in this particular case, this is so-called Crane extension. And this corresponding symmetric operator is nothing but as a closure of the second differentiation when we start from the space of infinitely differentiable functions vanishing at around 0. So apparently, this operator can be described by the condition f of 0 is 0, f prime of 0 is 0. Now, let's take an element from the domain of the adjoint minus the domain of the operator. Because on the domain operator, we have a Zeno state. In case A, for any element from this set, we have anti-Zeno state. So when I look at the system disappears. In case B, everything is a Zeno state. The picture is like this. In the first case, in the Friedrichs extension, we are looking at the critical domain, I would say. And if the state is taken from the red domain, the system will disappear immediately. In the second case, if I look at any element from the domain of the adjoint, all the states will be Zeno states. Apparently, it means that, not it means, but apparently any element from here has finite energy. That's why we have a Zeno effect. So here we have some kind of phase transition if we move from one type of boundary conditions to the other. Apparently, if we are dealing with the boundary condition of the third type, the story would be like in case B. So there is only one exceptional case, is the Laplacian, the Friedrichs Laplacian, Dirichlet Laplacian. So the second example is a massless particle on a ring. Very simple. We have a ring. We have L2 on a finite interval. I'm looking at the first differentiation operator. And I will pose, say, periodic boundary conditions or quasi-periodic boundary conditions. The minimal operator is obtained by taking the closure of the same guy, apparently. And then how to describe the domain of the adjoint. Apparently, the elements from the adjoint may have some some jump. And the answer is like this. If phi belongs to the domain of adjoint and doesn't belong to the domain of the operator, then phi is a Zeno state, is a resonance state with a decrement like the jump of the corresponding wave function from 0 and at point L. So if I'm talking about the circle, so this jump is between the value of the function from the left and the value of the function from the right. In the second case, we have that the corresponding decay constant depends on the boundary condition. Apparently, this boundary condition has something to do with posing some additional magnetic field, like a Aharonov-Bohm effect. And in fact, changing the flux of the field, one can change the value for the corresponding decrement. So, using the pictures, I would say that for this particular scenario, when our element is taken from the domain of the adjoint minus the domain of the operator, we have a green exponential decay. So I have shown you three possible outcomes. For massive particles, here we have anti-Zeno effect. I look at the system, immediately evaporates. Here we have a Zeno effect everywhere. I stop the evolution immediately. And here I'm looking at the system where a massless system, and the situation here is like this. I look at the system and the system actually decays exponentially. So I'd like to finish my talk by looking at one more example. And this is, of course, quantum harmonic oscillator. Quantum harmonic oscillator is supposed to be around every time. Otherwise, we don't know what we do. So I decided to change this operator a little bit, just edit 1/2 in order to make sure that the ground state is 1. And so this operator has discrete spectrum. It's well known that the spectrum consists of natural numbers, 1, 2, 3, 4, 5, and so on. The corresponding eigenfunctions are well known. They are related to Hermite polynomials and with exponential weight like this. And now I'd like to prepare some special state. And the state will be like this. I'll take those components, those eigenfunctions. The coefficients here are going to be 1 over n to the power s. And here I have some normalization factor in order to make sure, this is Riemann zeta function, to make sure that this element has norm 1. And that's why I'm dealing with a quantum system. And the answer here is like this. If S is from 1/2 to 1, then the corresponding state is anti-zero state. If I look at the state, it will immediately disappear. If S equals 1, we are dealing with a resonant state. So it means I look at the state and the state will be disappearing, following the corresponding exponential decay scenario. And finally, if S is huge, is greater than 1, we are going to have a Zeno state, Zeno effect scenario, exactly what has been discussed in the case of differential operators with different boundary conditions. By the way, the quantum harmonic oscillator doesn't require posing any additional boundary conditions because it is essentially self-adjoint on the natural domain of definition. So now, since I was talking about the exponential decay quantum mechanics, let's see how to write down the corresponding state if S is equals 1. So here we go. The corresponding eigenfunction looks like square root of 6 over pi. Euler proved that z of 2 equals something like this. And here we have the sum like 1 over n times the corresponding eigenfunctions. And therefore, this is an example of a quantum system that exhibits exponential decay when I watch what is happening with the system continuously. Under continuous monitoring, the system shows some exponential decay. However, the corresponding operator, the Hamiltonian, is positive, and moreover, it has discrete spectrum. So if I look at the decay without applying the concept of continuous monitoring, the corresponding decay will not be exponential. But if I watch the system using this suspicious behavior, very continuous monitoring, I will have the exponential decay. Now, let me show you some picture. That illustrates the situation. Apparently, with Eduard Tsikhanouski, we published a book this year called The Mathematics of Open Quantum Systems. And my talk was actually an attempt to illustrate the cover of this book. And the idea is like this. Look, we were dealing with a quantum system, like quantum oscillator. So symbolically, we have an animal called a cat, Schrödinger-like cat, sitting on the swing, and the swing is swinging. The cat has different hypostases. Apparently, you know, it is not only dead and alive, it has many emotional states like sad or excited, overexcited and stuff like this. I mean, I'm talking about this decomposition, infinitely many hypostases. And then I'm watching and try to understand what is going to happen with this poor cat. And what do I see? I see that the cat will be exponentially evaporating, vanishing. And what is left? And now we know what is left. Apparently, the answer can be found in the literature. This is his smile, or grin. So this cat is looking at us in a very sarcastic way. First, it disappears by itself. Then we see only his smile was green. And then this grin say goodbye. Thank you very much.
Thank you for a very interesting talk. Any questions, please? No questions. Okay. In that case, thank you again. Okay, next talk. Да, пожалуйста.
На самом деле, я хотел презентовать эту книгу университету в надежде, что кто-нибудь когда-нибудь ее прочитает. То есть, если вам что-то было непонятно в моем докладе, такая возможность разобраться, что происходит, имеется.
Спасибо большое.